Welcome to lesson 20 on power system analysis. In this lesson, we will continue with the power flow analysis. We will start with some computational aspects of Newton-Raphson load flow method. Then we will develop the fast decoupled power flow algorithm, and we will take up an example for solving fast decoupled power flow problem. On the completion of this lesson, you should be able to compute elements of the modified Jacobian matrix, develop fast decoupled power flow algorithm, and solve power flow problem using fast decoupled method. We will start with the power flow equations that we had developed earlier, where we had said that a real power injection at any bus k is given by P k, and P k is equal to V k summation n is equal to 1 to capital N y k n V n cos delta k minus delta n minus theta k n, where V k and V n are the voltage magnitudes at bus k and n. Delta k is the voltage phase angle at bus k, delta n is the voltage phase angle at bus n, and theta k n is the angle of the admittance between bus k and n, that is the angle associated with the element y k n, that is k n element of the Y bus matrix, and y k n is the magnitude of that element. Similarly, the reactive power injection at bus k is given by the relationship V k is equal to Q k is equal to V k summation n is equal to 1 to capital N y k n V n sin delta k minus delta n minus theta k n. From these relationships for Newton-Raphson load flow, we had developed the model where J into delta x is equal to delta p delta q, where delta p delta q matrix or the vector is given by p specified minus p calculated, which is a function of the state variables at ith iteration. So, this state variable, as we have already discussed, are the voltage phase angles and the magnitude value at all the buses. Similarly, delta q I, that is the change in q at ith iteration, is equal to q specified value minus q calculated value, which is a function of the state variables. So, state variable delta delta and delta v is solved using this relationship, where J 1, J 2, J 3, J 4 are the submatrices of the Jacobian matrix. J 1 is del p by del delta terms, J 2 is del p by del v terms, J 3 is del p by del q by del delta terms, and J 4 is del q by del v terms. So, now this calculated value is computed, and then delta p delta q is calculated, that is put here. J 1, J 2, J 3, J 4 are computed at the ith iteration state variable values. So, once we know these matrix, we know this using the solution for this linear system of equations A x is equal to b kind of a system. We can solve for this x, and this x is given by this. So, once we get this x at delta x at ith iteration, then we can find out x at I plus 1th iteration as, that is delta at I plus 1th iteration and v at I plus 1th iteration is equal to whatever was the value of delta and v at ith iteration plus the change which we have computed just now, that is delta delta at ith iteration and delta v at ith iteration. The Jacobian matrix, as I said earlier, is this J 1 is del p by del delta submatrix, J 2 is del p by del v submatrix, J 3 is del q by del delta submatrix, and J 4 is del q by del v submatrix. At the values are computed at ith iteration by substituting the value of the state variables at ith iteration. Now, we can calculate the elements of the Jacobian matrix. This we had done in the earlier lesson. So, for the diagonal elements for J 1, that is del p k by del delta k, we have the relationship as del p k by del delta k is equal to minus v k summation n is equal to 1 to capital N, where n is not equal to k. So, that is into y k n v n sin delta k minus delta n minus theta k n. This comes out to be equal to minus q k minus v k square into b k k. Similarly, J 2 submatrix, the diagonal elements del p k by del v k is computed as v k y k k cos theta k k plus summation n is equal to 1 to capital N y k n v n cos delta k minus delta n minus theta k n. J 3 k k, that is del diagonal elements of J 3 submatrix, del q k by del delta k is given by v k summation n is equal to 1 to capital N, n not equal to k, y k n into v n cos delta k minus delta n minus theta k n. And J 4 k k, that is diagonal elements of J 4, del q k by del v k is equal to minus v k y k k sin theta k k k plus summation from n is equal to 1 to capital N y k n v n sin delta k minus delta n minus theta k n. This is equal to q k minus v k square b k k. The off diagonal terms are obtained in like this: J 1 k n, that is off diagonal terms of J 1, del p k by del delta n, this is given by v k y k n sin delta k minus delta n minus theta k n. The off diagonal terms of submatrix J 2 is given by del p k by del v n is equal to v k y k n cos delta k minus delta n minus theta k n. Similarly, the off diagonal terms of J 3 submatrix del q k by del delta n is given by minus v k into y k n minus v n cos delta k minus delta n minus theta k n. And the off diagonal terms of J 4 submatrix del q k by del v n is given by v k y k n sin delta k minus delta n minus theta k n. Now, if we see these, the elements of the off diagonal elements of the Jacobian matrix as well as the diagonal elements of the Jacobian matrix, we find some similarity in the terms. We will see how we can take advantage of these similarities. Now, comparing term for J 1 k n and J 4 k n, the main difference is the absence of factor V n, that is the magnitude value of voltage at nth bus in J 4 k n. That is, if we see here, J 4 k n and J 1 k n are very similar, except that this V n term is not present in this. Similarly, if we see J 2 and J 3, again we find that J 2 is missing V n, whereas this J 2 and J 3 are very similar, except that J 2 is missing this V n. Also, there is a sign minus sign associated with J 3. Now, if we can take advantage of this similarities, our computation for the Jacobian matrix can be made much simpler. Now, this difference is coming why? The difference is coming mainly because the partial derivatives with respect to the voltage magnitude variables, all the elements of matrices J 2 and J 4 are missing the factor V n. That is, since these J 2 and J 4 are partial derivative with respect to the voltage magnitudes, therefore, the voltage magnitude term are missing in J 2 and J 4. Now, suppose we replace this del p k by del V n by multiplying it by V n, that is the magnitude value V n. So, we replace this by V n into del p k by del V n in J 2. Similarly, for terms for J 4 can also be multiplied by V n, and since these terms are on the left hand side of the equation is multiplied by V n's, I am sorry, this should be V n's, the corresponding terms in the update vector should be divided by the appropriate V n's in order to maintain the specified relationship. That is, what we have done is del q k by del V n we have multiplied by V n, right. So, what we are doing? We will this delta V n term we will divide by V n. So, then what we will get will be del q k by del V n into delta V n, which is the same term as the original matrix. So, what we are doing? We are multiplying the terms of the J 4 matrix by V n, similarly multiplying the terms of J 1 J 2 submatrix with V n, we will divide this delta V n term by V n, then we get the same relationship. So, the relationship or the equation is maintained by multiplying the J 2 and J 4 terms with V n and dividing delta V n by V n. Therefore, the relationship now comes out to be del p and del q at mth iteration, that is with the value substituted for x, which is delta delta and delta v, which is v and delta angles. So, x is v and delta. So, substituting the value for that in the equation for p and q. So, we will get p specified minus p calculated, and that will give me delta p and delta q at that state with that state variable. And the Jacobian now we have renamed, because we have multiplied the elements of J 2 and J 4 by V n. So, we have renamed these submatrices as H, N, M and L, where H is same as J 1, M is same as J 3, N is J 2 multiplied by V, and L is also J 4 multiplied by V, and also the term delta delta remains same, but this term delta V which was there is now divided by magnitude V, because we have multiplied the terms of J 2 and J 4 by this V. So, if we do this, then we have where we are saying is the, if we look at this J 2 into V, actually this V is basically a diagonal matrix of voltage magnitudes. Therefore, this V is defined as V 2, V 3, V 4. Here we are assuming that bus 1 is our slack bus. That is what we had been using from very beginning. So, bus 1 is considered as slack bus. So, V is V 2, V 3 up to V n, and delta V by V is delta V 2 by delta V 2, and so on, delta V n by V n. So, this is what we get. Then what happens is, we have now, if you look at this, we are calculating these terms. We know this, we have got the values of these by substituting the value of state variables, that is voltage, magnitude and angle in the for the elements of Jacobian. Then solving this expression, we can calculate delta delta m and delta V m by V m. So, once we have calculated this, then we can get the updated value for m plus 1th iteration as delta I, that is delta at ith bus for m plus 1th iteration is equal to delta I at mth iteration plus delta delta I at mth iteration, and similarly the voltage magnitude is updated as V I at m plus 1th iteration is equal to V I at mth iteration into 1 plus delta V I by V I at mth iteration. So, this is the update that we do. Now, if we look at this, what we have done here is we have modified our Jacobian matrix terms in such a way that we do not need to compute all the terms, that is we have J 1, if we compute the J 1 terms, we have also computed the J 4 terms. Now, similarly, if we have computed the J 2 terms, then we also have computed the J 3 terms. I am sorry, here there is a mistake, this should be J 3. So, sorry, this is J 2 terms, then we also have computed the J 3 terms if we have used this modification, that is we have multiplied the J 2 and J 4 terms by the voltage magnitudes. So, this is a great advantage because you do not need to compute a large number of elements of the Jacobian matrix. So, this speeds up the computation for the Newton-Raphson method considerably. Now, still Newton-Raphson method requires enormous amount of computation, though we use techniques for improving the computational efficiency of the Newton-Raphson method, because we know that the Jacobian matrix there are large number of elements which will be 0. So, we use sparsity techniques for solving this. We will discuss some of the sparse method techniques in the next lessons. There is still some chance for improving the computational aspect of the power flow problem, and this we can do by seeing some of the practical aspects associated with the power flow equations. We know that change in voltage angle delta at a bus primarily affects the real power P in the transmission lines. That is, delta primarily affects the real power flow in the transmission lines, whereas the reactive power flows remain more or less unchanged. Same thing we see that if we change the voltage magnitude, then the reactive power flow on the transmission line get changed, but the real power flow remains more or less unchanged. This shows that P and delta are strongly linked, and Q and V are strongly linked, and there is a weak coupling between P delta and Q V, and we can take advantage of this property of the power system in trying to improve the computational aspect of the power flow problem. And if we do that, that is, if we see the Jacobian matrix J 1, J 2, J 3, J 4, if we see this, we can also see, since there is a weak coupling between P and V, that is the voltage magnitude, we find that the elements of this J 2 submatrix, which is basically providing the sensitivity of real power, with respect to voltage magnitude, and similarly the elements of the J3 submatrix, which is providing, which is del q by del delta, that is sensitivity of reactive power with respect to the voltage phase angle. The elements of these submatrices J2 and J3 are much smaller compared to the elements of J1 and J4. This also tells us the same thing, that there is a strong coupling between P and delta and Q and V, and a weak coupling between P and V and Q and delta. And therefore, if we try to take advantage of this weak couplings, we can neglect the submatrices J2 and J3, that is, we can make them 0. So, we have now the Jacobian matrix consisting of submatrix J1 and J4 only. If that is the case, then we have the equations written as J1 delta is equal to P delta P. That is, if we look at this equation, since we have made these submatrices 0, so delta P is equal to H into delta delta H or J1 into delta delta, and delta Q is equal to L into delta V, or sorry J4 into delta V, or L into delta V by V. So, this is what we see. Now, what has happened is the set of equation, that is, if we assume that there is no PV bus, then we have 2 into n minus 1 set of equations, and the Jacobian matrix is 2 into n minus 1 into 2 into n minus 1 matrix. Now, here what has happened is, now this J1 term is only there, which is n minus 1 into n minus 1 matrix, and J4 term is there, which is again n minus 1 into n minus 1 matrix, if we assume no PV buses. Then what we have seen is this whole problem, which was a 2 into n minus 1 simultaneous equation, has been broken into 2 n minus 1 simultaneous equations, and this considerably reduces the computational aspect, because now our Jacobian matrices are much smaller, and solving for these takes much less time, because as we had talked about earlier, that the time taken for solving the Ax is equal to B matrix equation using Gauss elimination or some other method is proportional to n square additions and multiplications. So, the time taken is proportional to n square. So, now instead of 2 n square, which is 4 n square, now we are solving n square plus n square, that is 2 n square. So, the computational aspect we have gained considerably, that is, now we require only half the amount of computation in this case. So, now we have the relationship for the decoupled equations as delta P from bus 2 to bus n is equal to this submatrix J1 into delta delta from delta 2 to delta delta n. And for this the other set of equation is again this will be the submatrix L, which we are using because we have multiplied del q by del v by v. So, here we have del v 2 by v 2 and del v n by v n, and this is del q. So, this is the other set of equation that we need to solve. So, now the advantage of this method of decoupling has been that the computational aspect has been reduced considerably, but when trying to solve this, we find that the number of iterations required for this increases considerably, and in many cases there are convergence difficulties. So, this does not really help much. So, some other improvements looking at the physical aspects of the power system was suggested in form of a fast decoupled power flow method. Now, how this method was developed is based on certain assumptions which are valid for a properly operated power system. So, in a well designed and properly operated power transmission system, the angular differences, that is delta I minus delta j, between typical buses of a system are usually small. They are small. So, we have cos delta I minus delta j is equal to 1. Normally, this angle difference will be of the order of 10 to 15 degrees maximum, most of the time less than that also. So, we have therefore, cos delta I minus delta j very nearly equal to 1, and sin delta I minus delta j is approximately equal to delta I minus delta j radians. Also, the line susceptance B I j are many times larger than the line conductance G I j. That is true, because we know that the inductance of the transmission line is much larger than the resistance, and therefore, B I j is much larger than G I j. Therefore, we can say that G I j sin delta I minus delta j is much smaller than B I j cos delta I minus delta j, because this term will be more or less very near to 1. So, this term will be B I j, and G I j is much smaller, and sin delta I minus delta j is equal to delta I minus delta j radians only. Therefore, this whole term is much smaller than this term, and therefore, this can be neglected in comparison with this term. Now, the reactive power Q I injected into a bus I of the system during normal operation is much less than the reactive power which would flow if all the lines from that bus were short circuited to the reference. That is, if we short circuit that bus to the reference, what is the reactive power which will flow? It will be the voltage square multiplied by B I I. So, V I square into B I I is what will be flowing when we short circuit that bus to the reference, whereas Q I, which is the injected reactive power at that bus, is certainly much smaller in normal operating time. So, therefore, Q I is much smaller than V I square into B I I. In fact, this we can also see from this relationship, where Q k is given as V k into Y k and V n sin delta k minus delta n minus. Now, this Y k n into sin delta k n terms will give me the B terms, whereas let me go back and see this from another equation. Yeah. Yeah. Now, if we see this term for Q I, it will be V I V j into Y I j sin delta theta I j plus theta delta j minus delta I. Now, here what happens is this term will be a summation of all these terms, whereas we know that the term for Y I j is a negative term of Y I j, the actual admittance between the for the line connecting bus I and j, and B I I is a term which is sum of all the susceptances for connected to that line. That is, connected to that bus. So, susceptances for all the transmission lines connected to that bus, when we add them, we get BII, and Bij is negative of the susceptance which is connected to that between bus I and j. Therefore, if we look at this, the Qi, since it is summation of all those terms with summation Bij, Vi into Vj, therefore, Vi and Vj magnitude values will be very nearly equal to 1, and therefore, what we find is the total summation is going to be much smaller, because there are all Bij terms which are negative terms will be subtracted from Bii, and the total value of Qi therefore, is going to be much smaller than this. Now, these approximations can be used to simplify the elements of the Jacobian matrix. In equation, the off diagonal elements j 1 1 and j 2 2, that is j 1 and j 2 are given by del pi by del delta j is equal to Vj del Qi by del Vj. This is equal to minus Vi Vj into Yij sin theta ij plus delta j minus delta I. Using the identity sin alpha plus beta is equal to sin alpha cos beta plus cos alpha sin beta in the equation gives us del pi by del delta j is equal to Vj del Qi by del Vj. This is equal to minus Vi Vj Bij cos delta j minus delta I plus Gij sin delta j minus delta I, where we have used this Bij as Yij sin theta ij. This is the susceptance part, and Gij is equal to Yij cos theta ij, which is the conductance part. The approximations listed above yields the off diagonal elements as minus Vi Vj Bij. The diagonal elements of j 1 and j 4 are j 1 ii is equal to minus Qi into Vi square into Bii, and j 4 ii is equal to Vi into del Qi by del Vi, which is equal to Qi minus Vi square Bii. So, if we see these elements, applying the Qi is much smaller than Vi square Bii, that means this term is much smaller than this term. So, the expression for del pi by del delta I will be approximately equal to Vi into del Qi by del Vi, and both will be approximately equal to Vi square into Bii. So, this is what we see, that the diagonal elements will be given by this, whereas the off diagonal elements will be given by this. Now, if we take a 4 bus system where bus 1 is a slack bus, then we can write the expression for j 1 into delta is equal to delta p in this form as V 2 into V 2 B 2 2 minus V 2 into V 3 B 2 3 minus V 2 into V 4 B 2 4, and similarly V 2 V 3 into B 3 2 V 3 V 3 into B 3 3. This, that is what we have got is V 2 V 2 into B 2 2 into delta 2 delta delta 2 minus V 2 into V 3 B 2 3 into delta delta 3, and so on. So, this is the expression that we have got. These are the Jacobian matrix elements. Similarly, for the other expression, that is for L into delta V by V is equal to delta Q expression, we have got like this, which is V 2 into V 2 B 2 2 and in this form. So, now if we take up one equation, then we have say this equation for the first row, that is delta Q 2 is equal to B 2 2 minus B 2 2 delta V 2 minus B 2 3 delta V 3 minus B 2 4 delta V 4. This is what we will get. Here we had this term V 2 2, V 2 into V 2, V 2 into V 3, V 2 into V 4. So, what we have done is we have taken out that V 2 term and divided it here. Similarly, for the expression from here, again we will get V 2 2, V 2 into V 2, V 2 2 minus V 2 into V 3, V 2 3 minus V 2 into V 4, V 2 4 into this term into delta 2, this term into delta 3, this term into delta 4 is equal to delta P 2. Now, these V 2 terms in this, if we take out and divide on this side, the equation remains same. So, what that is what we have done. So, we have minus V 2 into B 2 2 delta delta 2 minus V 3 into B 2 3 delta delta 3 minus V 4 B 2 3 into B 2 4 into delta delta 4 is equal to del P 2 by V 2. So, from here we can now see, we can write this expression here like this, minus B 2 2 minus B 2 3 minus B 2 4 and so on into delta delta 2 delta delta 3 delta delta 4 is equal to delta P 2 by V 2 delta P 3 by V 3 delta P 4 by V 4 in this way. And similarly, for the other expression we have again minus B 2 2 minus B 2 3 minus B 2 4. So, this matrix we have this matrix which is containing terms of susceptance only. This is delta V 2. Now, this term that we had multiplied V 2 here and we have divided V 2 V 3 here. So, this we have taken out. So, this is again now a constant term, this is delta V 2 delta V 3 and delta V 4 and this V 2 we had divided. So, we are getting del q 2 by V 2, del q 3 by V 3 and del q 4 by V 4. Now, what we are seeing from these two sets of equations, that the matrix Jacobian matrix here is only the susceptance elements and therefore, these are constants. They are not dependent on the state variables and therefore, these remain constant throughout the different iterations. So, they do not change with the iterations. Now, if they do not change with the iterations, means we do not need to compute these elements each time. That is one advantage. The other advantage is, once we have triangularized these matrices, we can keep the matrix elements stored because they are not going to change, and what we need to do is only do a forward operation on this vector and then using a back substitution we can calculate the value of the unknowns delta v and delta delta. So, this is a great advantage that we get because the matrix is now a constant matrix. We can store the factors of this matrix or triangularized matrix and we can use them in each iteration. This considerably reduces the computational requirement for this method, and this is why this method is called a fast decoupled power flow method, because this is much faster and it uses a decoupled relationship, that is P delta and Q v relations are decoupled, that is P is decoupled from V and Q is decoupled from delta. Now, the algorithm for fast decoupled power flow is as such: calculate the initial mismatches del P by V, solve for delta delta, update the angles delta and use them to calculate mismatches del Q by V, solve the equation for delta V and update the magnitudes of V. and return to step 1 and repeat the iteration until all mismatches are within specified tolerances. That is, maximum delta p is less than some tolerance value that we have, and maximum delta q is less than some tolerance value. So, what we need to do is, if we see here, what we do is, this matrix is already available because we know the susceptances for the system. We can compute these elements and solve for this. Once we get these values, we add it to the previous values of delta, and so we get the new values of delta. Once we have got these values of delta, using this we will compute the elements of this vector, that is del q by v vector, right, and since this matrix is already known, so we will compute this by solving this equation. So, once we get this delta v's, we add it to the previous iteration values of v, and we get the new values of v, and then we go back and again compute these values with the new values of v obtained and solve for delta delta, and this way we keep on repeating the iteration till we find that the value of delta p for all the elements or all the buses and delta q for all the buses are within limits. So, if once that happens, then we have got the values of v and delta, and using this we can calculate all the power flows in the transmission lines, slack bus powers and PV bus Q values. Now, if we have any PV bus in the system, then the row and column for that bus will not be there in the matrix for this expression. So, the two matrices, this matrix is generally termed as a B dash matrix, that is B dash into delta delta is equal to del p by v, and this matrix is called B double dash matrix. So, B double dash into delta v is equal to del q by v. So, this is the expression that we have, and this is the algorithm that we use for solving the power flow using fast decoupled power flow method. Now, we will take one example for solving a power flow using fast decoupled method. So, consider the circuit shown on the next slide. The transmission line is represented as nominal pi equivalent network with series impedance Z L is equal to 0.0 plus j 0.1 and half line charging admittance Y c is equal to j 0.01. Using fast decoupled power flow, find the values of theta 2, theta 3 and V 3. Now, if we see this system, this is a 3 bus system. This bus 1 is a slack bus where the voltage is specified as 1 angle 0, that is 1 plus j 0. Bus 2 is a PV bus where we have the real power injection given as 0.6661 per unit, and the voltage magnitude at this bus is given as 1.04 per unit. Bus 3 is a PQ bus where the load value is given as 2.5 plus j 1. Now, using the transmission line impedance values, we have got B I j is equal to 10 for I not equal to j, that is B 1 2, B 1 3, B 2 3, B 3 2, all these terms will be equal to 10 because it is equal to 1 by 0.1, 1 by 0.1 j 0.1. So, that becomes minus j 10, and B I I is equal to minus 19.98 because we add all the susceptances connected to the bus plus the half line charging of the two lines at that bus. This we had already calculated in the previous lesson. So, I am just substituting those values. We have been given P g 2 is equal to 0.6661 and V 2 as 1.04. We have therefore, P 2, the real power injection at bus 2, is equal to P g 2 minus P d 2, the demand at that bus, since the demand at that bus is 0 or the load at that bus is 0. So, P 2 is equal to 0.6661. P 3 is P g 3 minus P d 3. So, P g 3 is 0. So, P d 3 is 2.5. So, P g 3 minus P d 3. So, P 3 is equal to minus 2.5. Similarly, Q 3 is equal to Q g 3 minus Q d 3. So, Q g 3 is 0 and Q d 3 is 1.0. So, Q 3 is equal to 0 minus 1.0, which is minus 1.0. Now, we have to find B matrix. So, B matrix is B 2 2, B 2 3, B 3 2, B 3 3, because bus 1 is a slack bus. So, here we have the values substituted. Now, for fast decoupled power flow, we have minus B into delta theta or delta delta is equal to del P by del V. So, and we have minus B into del V is equal to del Q by V. Now, we can take the inverse of above equations to get, that is, we can solve this by using minus B inverse into this will give me this, and similarly minus B inverse into this will give me this, that is delta theta or delta delta, whatever you write, at nth iteration is equal to minus B inverse into delta P by V at nth iteration. Or we can write delta theta 2 delta theta 3 at nth iteration. This is the value of B inverse. So, this into this will give me the value of this. Similarly, del V 3 at n is minus B inverse into del Q 3 by del V 3. Now, here this, since we have only V 3, that is bus 3 terms available. So, the in this case minus B inverse will be only the inverse of this term. So, B is given like this, and for the Q equation we have only for bus 3. So, bus 2 row and column is eliminated and we have only B 3 available. So, we using this we get del V 3 as this much. Now, we can calculate the value of injection at bus 2 and bus 3 using the value of V and theta or delta, that is the phase angle, using the expression for real power injection at bus 2 and 3, and similarly the reactive power injection at bus 3. So, once we take or assume a starting value, the starting value normally, as we said earlier, we assume as a flat start. So, theta 2 and theta 3 at the starting point is 0 degrees and V 3 at starting point is 1 per unit. The values of P 2 at the starting point, P 3 at the starting point and Q 2 Q 3 at the starting point can be calculated. I am sorry, this should be Q 3 at the starting point can be calculated from these equations. Substituting the values, we get P 2 is equal to P 3 is equal to 0 and Q 3 is equal to minus 0.42. Now substituting these, we can find the mismatches like this. So, we will have the mismatch values as 0.6661 minus 2.5 and 0.58, that is delta P 2 is 0.6661 minus 0, delta P 3 is minus 2.5 minus 0, delta Q 3 is minus 1 minus 0.42. So, this will give you delta P 2 is equal to 0.6661, delta P 3 is minus 2.5, delta Q 3 is minus 0.58. So, once we have that, then we have this del P 2 by del V 2. So, V 2 is given as 1.04. So, 0.6661 divided by 1.04 gives me this del P 3 by del by V 3. Now, V 3 is 1.0. So, we get this same as 2.5 minus 2.5 by 1, which is same as minus 2.5, del Q 3 by V 3 as minus 0.580 by 1, which is same as 0.05 minus 0.580. Using the value of mismatch matrix, we can calculate the value of theta 2, theta 3 and V 3 and continue the iteration process till we get sufficient accuracy. The results are shown here, that is the initial values we have theta 2, theta 3 as 0 and V 3 as 1, and these are the value of P 2 by V 2, P 3 delta P 2 by V 2, delta P 3 by V 3 and delta Q 3 by V 3. After first iteration, the values of theta 2, theta 3 and V 3 come out like this, and then when we calculate the new values, we get the new values like this. Again, using these values, when we compute, we get theta 2, theta 3 and V 3 like this, and when we find mismatches, we are getting like this. Again, substituting those values, we will get these values of as the angles and the voltage magnitude, and here we find that the mismatches has reduced considerably, and since we have used our tolerance value to be of the order of 0.005. So, these have converged. So, these are the final value of theta 2, theta 3 and V 3. Thank you very much. Welcome to lesson 21. In this lesson, we will continue with the power flow problem. In this lesson, we will first take up power flow problem for large power systems. How do we implement it? What are the implementation aspects? One of the aspects which we will look at will be sparse matrix methods and its application to power flow problem, and then we will also look into the modeling of regulating transformers in power flow problem. On the completion of this lesson, you should be able to explain the issues involved in implementing power flow solution for large power systems, apply sparse matrix methods to power flow, and develop regulating transformer model for power flow solution. Now, what are the types of power flow methods that we have learnt earlier? We have discussed about the Gauss-Seidel method for solution of power flow problem. Then we looked into the Newton-Raphson method. Then we tried to take advantage of the physical property of the power system, where the real power and voltage phase angle close association and reactive power and the voltage magnitude close association was taken into account, and the power flow equations were decoupled into P delta and Q V two sub problems. And then we saw that by taking certain physical characteristics of the power system. Now, let us see if we do the factorization for this kind of a matrix, what happens. Now, if we take a matrix like this that we have used earlier, the same matrix, and if we try to use the Gauss elimination method for factorizing this matrix, then after the first step of Gauss elimination, that is reducing all the elements in the first column as zeros, what we will have is all these elements which were 0 are now getting filled in. That is, instead of a sparse matrix, now we have a completely full matrix. That means sparsity is lost because we get large number of fill-ins in this case. Now, let us see what we can do about it. So, if we are trying to take advantage of sparse matrix and we want to use this sparse matrix method, if we go through the factorization just like that for the given matrix, then we find that the sparsity is no longer maintained because large number of fill-ins will come. So, what do we do to minimize these fill-ins? So, to minimize these fill-ins during the reduction step, the matrix needs to be reordered or renumbered according to the number of non-zero elements which in each row, which we call the row's valence. So, if we take any row and see how many non-zero elements are there in that row, and we call that as the row's valence. So, if we pick up the rows which have minimum number of non-zero elements, or the rows with minimum valence are ordered as row number 1, and so on we go till we reach the last row which will have the largest number of non-zero elements. Then we will talk about the regulating transformers and how we can model them in a power flow solution, and then we will see some comparison of the Newton-Raphson load flow and fast decoupled load flow algorithms. So, with this we will stop today, and we will take up in the next lesson the other things as I discussed just now. Thank you very much.